Okay, so we're going to have a look, guys, at a video on part of the energetics topic from AS level chemistry, and we're going to look at using experiments to work out the overall delta H of a reaction. And then when I talk about experiments, I'm talking about the coffee cup calorimeter experiment and the fuel burner experiment, which we use to work out the enthalpy of combustion. And we'll have a look at those two experimental setups in a little minute. I just want to have a look at some, but not all of the definitions that you need to be aware of for this. So we'll look at the enthalpy of a reaction, which is just the enthalpy change in a reaction based on the number of moles that you actually use in that reaction. So it would be maybe A plus B to give you C plus D, the delta H or the enthalpy change for that. Okay, based on the moles of A and B used. Now you'll most likely be asked to scale that up to per mole, so frequently up to kilojoules per mole of either A or B, or maybe even per kilojoules per mole of C and D that are actually made in there. The next one is your definition of enthalpy of neutralization, delta HM, which is the enthalpy change when you react an acid and an alkali together. I haven't written this all out, it'll all be in your notes. The enthalpy change when you make 1 mole of water when you react an acid and an alkali together. So when you react an acid, H plus, an alkali, OH minus ions, and you get 1 mole of water produced. And the next one that we're going to look at in this little video is the enthalpy of combustion, which is the enthalpy change when you burn 1 mole of a substance, okay, in excess oxygen, and in doing so you'll get carbon dioxide and water. Okay, so those are the sort of the definitions, and if you have your notes with you, it's a good idea just to keep those definitions at the side, because I'll probably refer back to them quite frequently in this little video. Okay, so the first thing is, well, how do we actually do this? How do we get a calculation to give us an enthalpy change per mole of something in a reaction? So we'll look at this particular type of apparatus first, which you may well have come across. This is just a little coffee cup calorimeter, your insulation vessel. We probably used a polystyrene cup. This is your reaction mixture in here, which will probably be 2 solutions, okay, all together, although it may well be just aqueous solution, so it may well be a certain volume of water, okay, plus some solids. You might be reacting a solid with some water, or you might be reacting a solid with another solution in perhaps a displacement reaction. Okay. You've got a thermometer obviously to measure whether the temperature goes up or down. Your coffee cup calorimeter is usually a polystyrene cup. If you wanted to improve it, sometimes you could use 2 polystyrene cups. We've got a lid, hopefully a polystyrene lid, or a lid that can keep some heat in. Okay, and you've got obviously your reaction mixture. So it's a fairly rudimental kind of a setup here, but it does have the purposes for AS chemistry, but there will be places where you lose heat and you lose accuracy, so you need to be aware of those. Obviously a polystyrene cup, even if I hold a cup of tea in a polystyrene cup, some heat and my hand will feel warm, so clearly some heat is escaping. So that's an error that you want to quote. Some heat would also escape from up there, and heat will also escape into the air around us. So not all heat makes its way into the thermometer, unfortunately. So you have a few sources of error there, but it gives us a fairly reasonably accurate assessment of what's going on in here, and allows us to carry out the calculations to work out the delta T. The delta T and then the enthalpy change. Right, so let's have a look at how we actually do the calculation. So the first calculation that we do when we carry out a reaction is do Q equals M multiplied by C multiplied by delta T. So it's important that we know what these things are. Q is simply the energy change that is going on inside that reaction, and that is measured in joules, and that's important because our final answer of enthalpy change is in kilojoules per mole, so we'll have a conversion to do at some point. M is simply the mass of the solution which is absorbing the heat, and that's important in terms of the volume. We need to realize that water and most solutions in this are treated as having 1 cubic centimeter equals 1 gram. Okay, so in other words, the volume is equal to the mass in grams. C is the specific heat capacity of water, and that's really a correction factor because obviously water will itself absorb some of the heat. So that's the specific heat capacity of water and allows us to correct our calculation for the heat that is absorbed into the water and doesn't make its way into the thermometer. Okay, I suppose it should really be the specific heat capacity of the solution, but it's more often not water, and it's usually just quoted for water. That is 4.18 or 4.2. Read the question carefully because one of those values will be quoted. And delta T is just the change in temperature, so the initial reading minus the final reading that you get on your thermometer. So when I talk about the solution that's absorbing the heat, I'm talking about this solution in here, guys. So if that was 100 cubic centimeters, okay, then our M, our mass, because that's 1 gram per cubic centimeter, would be simply 200. Okay, our delta T will be given here, and our specific heat capacity is quoted in the question, usually at 4.18 or 4.2. So we'll have a look at some of these enthalpy changes with regards just using solutions like we have for the coffee cup calorimeter, and then whenever we have finished those, we'll move into working out the enthalpy change for some enthalpies of combustion using this little spirit burner or fuel burner that we have down here, this type of apparatus here, which is not a whole lot different, but there are certain fundamentals that are different which affect the way in which we do the calculation. Okay, so we'll just take a very simple reaction to begin with between, let's say we'll take a displacement reaction where we have a reaction carried out of zinc solid being added to some copper sulfate solution. Okay, we are going to start off with, let's say, 6 grams of zinc, and that's going to be in excess. Okay, and we're going to add that to 50 cubic centimeters of 0.1 molarity copper sulfate, and hopefully we know the reaction here is a displacement reaction, and we will get so we're going to be asked to work this out as an enthalpy change and work it out in kilojoules per mole of the copper sulfate. Okay, the zinc is in excess, so we don't work it out with regards to the zinc. So our first step in this is to work out Q, and Q equals M. M is 50 because 50 is the volume of the solution absorbing the heat. Okay, we'll say the specific heat capacity is given to us at 4.2, and delta T, let's say the temperature, the initial temperature was 20 degrees Celsius, and the final temperature was, we'll make it a nice round number, of 25 degrees Celsius. Okay, so that would be a delta T, therefore, of course, of 5 degrees Celsius. So our Q is 1050, and remember that is in joules. So the amount of energy given out, if I carried out that reaction, so if I had zinc sulfate in here and I added 6 grams of zinc into it, or sorry, 6 copper sulfate in here solution, and I added 6 grams of zinc into it, okay, stirred it up, took the temperature, okay, that is my Q value. But I've been asked to work it out per mole of the copper sulfate. So at the minute it's not per mole, so I need to find out how many moles of copper sulfate caused this increase in temperature. Okay, well, remember N equals C times V over 1,000 because I've got volume and concentration of my copper sulfate. So that gives me moles of copper sulfate at 0.005 moles. Okay, now the next thing that I'm going to do then is to work out my delta H, and remember my delta H is given in kilojoules per mole. So I'm going to take this and convert it into kilojoules, okay, just by dividing by 1,000, and then I'm going to take this and I'm going to convert it into kilojoules per 1 mole of copper sulfate, although it will also be of zinc because they react in a 1-to-1 ratio here. So I'll take my 1.05 and divide it by 0.005, and that will give me a value of 210 kilojoules per mole. Now don't forget that this is an exothermic reaction. I said the temperature went up, as it did, by 5 degrees. So you've got to make sure your final answer has got a negative value on it to show that you understand that it's an exothermic reaction. Okay, so that's first one, pretty straightforward. We'll do another couple, and hopefully you'll be able to go away and do some questions and apply the principle. Okay, so we'll just get rid of that. This time we'll take a look at a neutralization. Okay, so a neutralization would be a reaction between an acid and an alkali. So we'll take sodium hydroxide reacting with sulfuric acid. Okay, and that will give us sodium sulfate, and we will get water. Now if you remember back to our definition earlier, an enthalpy of neutralization, a delta HN, is the enthalpy change when an acid and an alkali react together to make 1 mole, and I'll just write part of it out here, to make 1 mole of water. So let's say the examiner says we've got 50 cc's of sodium hydroxide at 0.25 molarity, and we've got 50 cc's of sulfuric acid at 0.125 molarity. Okay, we'll say our initial temperature was 21 degrees and our final temperature was 33 degrees, giving us of course a delta T of 12 degrees. Okay, we'll say our specific heat capacity is given to us this time at 4.18. Okay, so let's go. We need to do first of all work out Q equals mc delta T. So Q equals m. So remember we did this in our coffee cup calorimeter and we added the acid to the alkali. So our total solution in here would be the two solutions together, which would be 50 plus 50. A lot of people get this wrong because they just write 50 multiplied by 4.18 multiplied by our delta T, which is 12 in this instance. So we will get a Q value this time coming out at 5,016, and remember put your units on it, that is kilojoules. Now they're going to ask us for the enthalpy of neutralization. Okay, so delta HN, which is going to be kilojoules per 1 mole, and that's going to be per 1 mole of the water. So how do I work that out? Well, my moles of acid are, I'll just write it in here, N for number of moles are 0.00625. Okay, and my moles of my alkali are 0.0125. Okay, now I need to work out how many moles of water I will make. Well, I need to just check that nothing's limiting or in excess. So 1 mole of one mole of acid will require 2 moles of sodium hydroxide. So 0.00625 moles of acid will require double that, which is 0.0125 moles of sodium hydroxide. So these are in the right stoichiometric ratio, and one is not in excess over the other. So it doesn't matter therefore which one I use to work out how many moles of water will be made. It would be sensible if this is a 2 to 2 or 1 to 1 ratio to use that one. So I will therefore make in this reaction that number of moles of water, 0.0125. So up here I've got Q, I've got 5016 joules made in here. So I'll just very quickly convert that into kilojoules, because that's what my final answer has to be in. And I've got to convert it to make it up to per 1 mole of water. So I would take that and I would divide it by that. Okay, so will give me a final answer of 401.28, and we've already converted it into kilojoules, so it is now kilojoules and it is per mole. The temperature, if you remember over here, it went up, so we've got to make that a negative calculation or a negative value to show that we understand that it's exothermic. Okay, so those are a couple guides that we would come across quite a bit in terms of just solutions, and ones that we can use our little coffee cup calorimeter for there, and hopefully that gives you a good and reasonable understanding of where you can maybe drop marks and things that you need to just be a wee bit cautious of. Right, so we'll have a look now at doing the same thing. We're going to work it out for an enthalpy of combustion, which, if you remember earlier, is when you deltaT, enthalpy of combustion, is when you burn something in excess oxygen. Sorry, when you burn 1 mole of it in excess oxygen. So obviously we can't do that in a coffee cup calorimeter because it's made of polystyrene, and it wouldn't last long if I started to burn a fuel in it. So we use a different type of apparatus here completely. Well, no, not completely. We use a variation of it, I suppose. So we have our spirit burner down here, which will hold our fuel. Okay. And that heat is transferred when we burn it from here up into probably a copper pot is what you often use, and it can be very often, as we've shown here, insulated. You will frequently see as well what we call draft shields, okay, just to prevent any convection currents passing through and taking any of this heat away. Again, you'll need to be aware of where you can lose heat, and you can lose heat in the same places as earlier, into the air above, into that. Okay, convection currents here. You also get chemical loss here, because you get, as hard as you might try to get complete combustion, you get a bit of incomplete combustion and some other side products made here. So you may not be getting total complete combustion, which is what you should be getting in your for your definition. So let's take maybe we say we've got some ethanol, okay, and we're going to burn our ethanol. Okay, excess oxygen, and that'll give us carbon dioxide, and it'll give us some water. So we 4,7. So we balance that out as so. So if we imagine our little spirit burner, what we'll do with our spirit burner is we'll weigh it at the start and we'll weigh it again at the end after we've burnt it. Okay, and we generally keep a little lid on it at the start and the end to prevent any fuel in here, which tend to be quite volatile, evaporating off. So let's say we started with our little spirit burner and our water up here. We had, I'll try and keep this on the board. So let's say we had 250 cubic centimeters of water there. Let's say our temperature went from 20 degrees Celsius to 35 degrees Celsius, and our water is specific heat capacity of 4.2. So we'll use those values to work out Q as well. Let's say our fuel burner at the start had a mass INI for initial. We'll say it had an initial mass of 40 grams, 40.0 grams, and it had a final mass of 39.0 grams. So we'll make it nice round numbers. Now, where a lot of people fall cropper here is that because we have a mass here now of 40 and 39, a lot of people go mass equals 1 gram, so they do 39 away from the 40. But remember, the mass is the volume of the solution, or the mass of the solution absorbing the heat. And that is this here, this 250 cubic centimeters. That's the solution absorbing the heat. We'll come to this mass here in a little while. So therefore my Q here equals 250, not 39 away from 40, multiplied by 4.2, multiplied by our temperature has gone up by 15 degrees Celsius. So that gives us a value of 15750. So pretty big, but we are burning something here, so we probably do expect a slightly larger value. Remember again, our units are important, and they are joules at this time. So we're being asked to calculate the enthalpy of combustion. And if we remember that, that's when you burn 1 mole of something. Okay, so how do we know how many moles of ethanol are responsible for burning here? Well, we had 40 grams to begin with, and we had 39 grams at the end. So the heat given off here is from 1 gram of ethanol. So we can turn that into moles by doing mass over the relative formula mass. Okay, so we have 1 gram over the relative formula mass of ethanol, which is 46. So that gives us moles in here 0.217. Okay, so 0.217 moles of ethanol give us this amount, or this amount of energy. So the first thing I'll do before I convert it into kilojoules, before I convert it into a standard enthalpy of combustion, is I will convert it into kilojoules. Okay, and then we want to scale this up to per 1 mole of, in this case, ethanol. And therefore we divide it by the moles of ethanol. So that is 724 kilojoules. Okay, and obviously the temperature has gone up here and it's combustion. So our final answer, which would be our delta HC, is 724 kilojoules. Sorry, I need to write that on. Per mole. It's per mole of the ethanol, obviously, because that's what you're burning. Alright, so very similar calculation, but slightly different, and there's a few little areas where you can fall into places where you can sort of lose marks. I suppose this mass here, the most frequent one is people using this mass here for their M in their Q equals MC delta T calculation instead of the volume of the water that's in here. Okay. Sorry, I should have noticed there actually on my diagram there's a draft shield here. Actually I scribbled one in there, but there's already one on there. So yeah, just be aware guys, not only of how to do the experiment and draw the apparatus and label the apparatus, but how to do the calculation, but also be aware of how you can actually lose heat in here and therefore produce inaccuracies in your experiments. Okay, I hope that is of some use to you in terms of energetics, Q equals MC delta T calculations. If there's any queries that you have, just come and see me please.